let me get started. Those who didn't share the day yesterday with us, my name is Matti Latvaho, and I'm the General Chair for the 6G Wireless Summit, the first one. And the background for having this summit is in our 6G flagship program that started last May. And we have decided to start to organize this annual event, hopefully through the lifetime of this flagship program, which is 8 years. So the plan is to have this as an annual series of events. Now that we are doing this first time, and admittedly, it's a bit early to talk about 6G since 5G is not yet deployed. It had been, in the beginning, it was a bit difficult to discuss with, especially with industry, anything beyond 5G. But we started bravely to have those discussions with different players, and I'm happy to see that today we are going to have some early visions and views from manufacturers and operators in particular. How do they see the future? Where do we have to aim next when we are building the infrastructure and services for 2030s? This keynote session, we have 2 keynotes from our gold patrons, Nokia Bell Labs and Huawei. We start with a presentation from Nokia Bell Labs, Peter Vetter, who is head of the Access Research Lab and is Bell Labs fellow. Peter has been working since '93 for Alcatel and since 2009 at Bell Labs in Mary Hill. And he has been in senior leadership team of Bell Labs since 2013. So he has a good view on Bell Labs' visions for the future. So, Peter, floor is yours.
Good, so thanks for this kind introduction. Pleasure to be here, and thanks for inviting Bell Labs to share a first view on 6G. We are 2019, the year of first commercial rollouts of 5G. We have heard yesterday that there are many innovations still in the pipeline for 5G, for future releases, a lot of work to do. We will make the point later on that 6G is actually still a decade away, and yet we have the audacity to put a big, giant 6 on stage here. Are we already overhyping the next generation while we're still working on the existing generation? Are we shooting ourselves in the foot? No, but as Matti already said, we have to have this discussion in the right context. It's a research discussion, a vision, a direction for future research, because as history tells us, the next generation is a decade away. The commercial rollouts will start in around 2030, and it needs to be good for a decade after that. So it's really for the 10 to 20 years to come. And as with many inventions, it actually takes 10 to 20 years before they see the commercial daylight. So it is absolutely the right time to start about the new technologies. But when you do research on new technologies, you also need to think about the right applications. You need to solve a human need problem. You need to create value with your new technologies. Hence the title of this presentation. But before going into the value creation and also coining already a few new technologies that may be of value for 6G, let's start with a bit of history. I'm proud to say that I work for Bell Labs in New Jersey. Even though I have no personal merit in it, it's the place where cellular networks was invented. In 1947, there was a memo going around by Ray Young and Doug Ring. What's in the name? Ring. They wrote a memo, and the people here in CC, they got a true carbon copy because email didn't exist in those days. And that memo laid out a solution to provide a wireless service across the nation to any equipped vehicle. And it detailed how you can efficiently reuse spectrum. They basically discovered the hexagon. 1947, by the way, same year as the invention of the transistor. Now it took many, many more years to reach mobile telephony. And it was actually this guy that pioneered it, Marty Cooper. He's not with Bell Labs, he was with Motorola. And he drove a research project that truly worked on a mobile handset. Remember, Ray Young and Doug Ring talked about equipped vehicle. So the project was called a phone in a shoe. I think it was inspired by a TV series of a secret agent, Maxwell Smart. And basically he built this brick. Battery charge time took 11 hours, 35 minutes talk time. He knew it was not practical. He wanted to show it could be done. And last year at the 5G Brooklyn Summit, he was there because he got a Wireless Pioneer Award. And at the dinner, he was telling the story how they hooked up an antenna in New York at the AT&T network, and he basically made the first wireless phone call to his competitor at Bell Labs. Basically to say, He was the first. But Bell Labs played an important role in the subsequent years to then build the first commercial networks. And to my earlier point, it took another 10 years before commercial deployment took off. Now, these first phones were analog mobile phones. The quality was not so good, and they were horrendously expensive. They were a status symbol. These were the days where you could actually observe at a crossing that some people would pick up their phone, and actually there were many of them, and you knew there was not enough capacity for them, so they were probably showing off. Some of them maybe even had a fake phone, a status symbol. The democratization came with the digitalization of mobile telephony in this country, the first GSM call with the Prime Minister in 1991. So this allowed us for scaling the mobile connectivity and getting the prices down. This was also the start of the success story of Nokia mobile handsets. And so since then, our industry has turned out a new generation of mobile telephones about every decade. And every generation was characterized by new radio technologies, new platform technologies, and new defining applications. New radio technologies that were aiming at broader bands, reaching for higher frequencies. And interestingly, so as you could maybe read in my bio, my background is fixed networks. Also in fixed networks, we had these same generations and approximately the same bandwidth going from generation to generation. And that is because we relied on the same underlying silicon technology with the same DSP technology. And also both fixed and mobile relied on the same network platforms of the day. Analog, then synchronous digital, asynchronous transfer mode, packet network technology, SDN. And we had the defining technologies that drove applications that drove the specification of the new technology. It's important. But then, as history told us, there's also the unexpected uses canonical for each of these generations. So now we are at 5G. The characterizing application is now for the first time industrial use cases. So the first 1 to 4 generation were actually driven by consumer use cases. Now for the first time we're talking about industrial use cases. We're just starting to roll out 5G, so we don't know yet what the unexpected use will be. But the important takeaway is the next generation is still a decade out, 2030. And we already have some cool ideas of technologies, but it is important to also start thinking and start a discussion on what will be the driving applications that we want to design for. And this is always important in research. You need to solve with your technology a human need problem. This is what has driven research for almost a century in Bell Labs. What is the human need problem? How do you improve productivity? How do you create value? So let's have a look at a metric, productivity, over the past century. This is from a book, Rise and Fall of Economic Growth. And it will appear soon. The animation had a bit of a hiccup here. But what we will see is the productivity growth over the past century. And in the first half, we see actually year over year that the productivity growth increased, thanks to inventions of the second industrial revolution, new transportations with automobiles, petrochemistry, new machines, power distribution, and telephony. Now, in the third industrial revolution, with the invention of the transistor, that starts with the invention of the transistor, the information age, the internet, mobile telephony, we see that productivity growth year over year is asymptotically going back to zero, going back to stagnation. This is worrisome. So what is behind that? So despite the internet, despite mobile networks, it's because we have been designing these mobile networks and the internet for consumers. Now, have a guess. In mobile, what is the fastest growing application today? The fastest growing mobile application today. Any ideas? Gaming, not anymore. E-commerce, very close, very good. Indeed, the fastest growing application is shopping. So this is from a report from Mary Meekers. She turns out every year an interesting report on internet trends. The fastest growing application is shopping, e-commerce. It has overtaken entertainment. Both of them are spending money. It's not productive. Gaming is even on a decline. Now, there's already hope on the horizon. More industries like financial and utilities that are the runner-ups here that start to embrace mobile networks and internet to enhance the productivity of their processes. So we can actually look at the industry in two canonical industries. There are the digital industries that already embrace the digital technologies. They represent today about 30% of our total economy. They invest 70% of the total spent in IT. Opposed to that are the physical industries, so digital industries like finance, like content creation industry, banking. Then we have the physical industries, retail, construction, transportation. They're representing 70% of our economy, but only a spend of a total of 30% in IT. Now compare their productivity. The blue bar is the digital industries. They have that healthy near to 3% growth year over year of productivity. The physical industries hovers around the sub 1% productivity growth. And now going to the era of Industry 4.0, the whole idea is to bring digital technologies to these physical industries so that they also can have that healthy productivity growth, enhance and automate their processes. And there is, for instance, a physical industry that already did that very well with Amazon, the way they commercialized their retail and transformed the retail industries. Now, this means that we need to change the way we think of designing the network. The internet and the mobile networks in the Industry 3.0 era have been designed to connect many mobile phones to servers in the central cloud. And on those servers, we have these platforms that run the e-commerce and the entertainment distribution. And all that basically worked very well on best effort networks. Now we go to Industry 4.0. Industry 4.0, where we now are going to connect everything. Machines, robots, cars, and mobile phones, by the way. And those machines now have response times that are a lot faster than humans. Humans have a response time of 100 milliseconds. So it was perfectly okay to have these servers in the central cloud. Humans would not experience that latency. Robots, on the other hand, have response times of milliseconds. A robot that moves in a factory at a meter per second, which is not fast, and you want to do that with a millimeter precision, you basically need a control loop of a millisecond. So that means that these things will still connect to the network, but those that need critical control processes that run in that, on those servers need to be much closer in the edge of the network. Then these control processes are very diverse, and they're meant to automate the whole factory or the autonomous driving. So they will be platforms enhanced with augmented intelligence. And now the communication becomes very critical. It's no longer best effort. We will see high-performance networks with very critical KPIs and SLAs. So there's actually two industries that are coming together in a very interesting way. We talk about the operational technologies that run factories and harbors and retail stores. And on the other hand, we have the ICT technologies, the information communication technologies. And they all have their, at a 30,000 foot level, the same values, but if you look closer, there's different interpretations of those values and characteristics. And they're coming together in an interesting way. So let's start with reliability. We talk in ICT about carrier grade. Now, carrier grade in LTE networks, what's the reliability of the network? Any guesses? So it's 99.8%. So 1 in 1,000 call drops, 2 in 1,000 call drops, and we call that carrier grade. For a factory, that's not good enough. A factory line that stalls costs millions because of a fault. So the operational technologies talk about reliabilities of 5 nines and even 9 nines. Then the technologies in ICT are very general. We have mobile phones and need a high level of standardization. On the weekend, I was in Copenhagen, connected there to the network. Now I'm in Levi. Tomorrow I will be in the US. And I'm able to roam into different networks of different providers, probably connecting to systems from different vendors. So standardization, very generalized global solutions. The operations technologies, they require very specialized solutions. Very specific solutions. A car manufacturer is very different from operating a power plant. It's very different from a warehouse or a retail store. So they require very specific solutions. So if we think of next generation networks to support these, we need to think of platforms that allow for instantiation of very specific networks that fulfill the specifications of specific interest groups. And so, and also flexibly configuring network instances in a very specialized way. Then the services that ICT provides, as I says, delivery of information, entertainment. Now we go to operational technologies. The types of communication will be very different. We need to track the state of machines, the location of assets. We need to send control messages in order to optimize the operational processes. Very different. Now, because it's so specialized, because it's so critical, the operational technologies is actually a very slow-moving industry. The car manufacturing line pretty much looks the same since Ford. Okay, in the last 10 years we have added robots instead of humans, but the manufacturing line looks very much the same. Containers in harbors, as long as I can think, they use containers for transportation. So very slowly changing industry. Our industry, on the other hand, is a rapidly moving industry. Every 10 years there's a new generation of mobile network technology. in data centers, we change technology every year and even less than a year. So by bringing these worlds together, we actually bring some of that dynamism into the operational technologies realm. We will allow for new robots to enter the factory thanks to wireless communication very rapidly, install sensors very rapidly, and then also allow for the factory to reconfigure in a dynamic fashion according to very different specific needs. Now, to prove that this is important, I want to quote here a report from McKinsey that predicted the global size of the market for digital automation by 2025. My colleague Lauri already mentioned this report yesterday. It says that the total size of the market is around $4 to $11 trillion. That's huge. There's a high uncertainty still, but it's huge. It's more than 10% of the total economy. And to put that in perspective, not all of that is, of course, for the network technologies. My colleagues from Bell Labs Consulting have estimated that about 1 trillion to 2 trillion is for network technologies in there. Still huge. Our current market today is 1 trillion. So by embracing this new opportunity, we basically can double the market size. Now, another proof point is the analysis on the left-hand side that you have been able to read in the meantime. It's the number of base stations that you will need for wireless connectivity for automation. The biggest ones are factories and warehouses, and the total is around 14 million base stations. Compare that to 7 million base stations today. Again, a proof point that this is an important new opportunity. An important new opportunity that, however, comes with very stringent requirements. And here are some of the requirements, and I'm not going to read through them, but on the second column you see requirements for time-synchronous networks that my colleagues got from various sources. And the main point is that these are a lot more stringent than what we are currently discussing in 5G for release 16. So for instance, the synchronicity now is not sub-microsecond, but sub-nanoseconds. The time cycles are no longer milliseconds, but tens of microseconds. The latencies are in that same order. It goes into the sub-millisecond and tens of microsecond range. And very important, determinism. The jitter is now in the sub-100 nanosecond range. So very stringent requirements that drive our networks and the design of the architecture. So in addition to the capacity bandwidth dimension that we have historically been focusing on for our research, we now need to focus and are already focusing on the latency dimension. And this graph maps the different applications. The icons speak for themselves. The main point is that until now, generation 1 till generation 4, we've designed for consumers. So basically for the blue quadrant, where 100 of millisecond latency was sufficient, and 10 of megabit per second for video was sufficient. Now we go for higher capacity, enabling 360 video representation and recording through 3D recording. And then in the latency dimension, we see the millisecond and even sub-millisecond latencies coming for critical control applications. And then there are the combinations of these two. For instance, for autonomous vehicles, where you have high bandwidth sensor data and then critical control messages going to the trucks or cars that you are driving. There's also an icon there hinting at radio technologies. We are, in fact, already designing networks with these requirements in mind. For centralized RAN, we need hundreds of microsecond latency. We need ultra-high capacity. So the interesting thing is we are already designing networks with these requirements in mind, and we can use that same architecture already in the 5G area for future automation to embed critical control applications in the edge of the cloud within less than a millisecond away from the device. So already today, we design networks with this ultra-low latency and high capacity in mind. And physics will dictate also how we design networks going forward. On one hand, we have capacity, and there's 3 fundamental dimensions that we can work with to enhance capacity. Shannon already told us that. We represent that in the triangle of truth. In the spectrum dimension, we go already to mid-band and high-band. In the efficiency dimension, we have better technologies for massive MIMO that improve the bits per second per hertz. And we have then the spatial dimension where we reuse frequencies by going to smaller and smaller cells and actually also having beams for simultaneous use. In the latency era now, physics basically dictates speed of light. So for human response times, 100 millisecond speed of light over a fiber round-trip time means you talk about distances up to 10,000 kilometers. So it is perfectly okay to have a server on the other side of the continent, and if you make abstraction of queuing delays, you will not experience the delay. For machines, very different. Now we talk about milliseconds and less. The servers that have the critical control applications now need to be away less than 100 kilometers, as that diagram shows. So we talk about edge cloud architectures. Let me dwell a bit more on what are potential new technologies further along those lines. So first, on the capacity, we already talk about increasing the spectrum from the tens of gigahertz. In release 17, we talk about 100 of gigahertz, and we are already venturing in research towards terahertz. My colleagues have built a 93 gigahertz large-scale antenna array system, millimeter wave beamforming. We are currently trialing it with Docomo. And we already have a chipset for 140 gigahertz. And we're also already working with academic partners on terahertz. Now, going to the spatial dimension, we talk about small cells today, 100 meters away of end users with millimeter wave. We can expect if the cost of these technologies goes down, that you will have much more ubiquitous availability of those radio access points. Our research team is working on low-cost massive MIMO technologies that will be very cheap and easy to install behind picture frames, billboards, so that they are ubiquitously available. And the flex foil allow for easy manufacturing and also easy installation even on curved surfaces. And then in terms of efficiency, we already made a lot of progress for 5G. We have massive MIMO with zero forcing. We have distributed massive MIMO thanks to the 5G specifications. For the research for next generation networks, this is a call, and we are already looking into this in a new integrated end-to-end approach, where we look at the total chain of the radio system, the power amplifiers, the fiber backhaul, the digitization, and the processing, and looking at it in an integrated way to improve efficiency of the signal, but also improve energy efficiency and cost efficiency. Now, this same triangle of truth is also an interesting guideline, not only for capacity. It can also help us to understand what we can do to improve reliability. For instance, on the efficiency dimension, we can now use or trade efficiency for more robust modulation, for better and more robust coding schemes. In the spectrum dimension, we can have channel redundancy on different frequencies. And in the space dimension, we can think of path diversity and joint transmission from multiple access points. Similarly, in latency, to improve latency, we can think in the efficiency dimension of more efficient scheduling protocols. In the spectrum dimension, we work with broader subcarriers, shorter symbols, shorter frame times. And in the space dimension, it's basically path length, speed of light. So just as one example of what we do in that space for reliability, with the challenge of getting to 9 nines, we will have to embrace path diversity. And how do you do that in a cost-effective way if you have only one single access point? Well, you use devices on the different robots or machines, different things, as relays to create path diversity, but at the same time, you need to meet the challenge of the sub-millisecond latencies. So until now, I talked a lot about connectivity, using radio for connectivity. And we all see ubiquitous availability of radio with small cells, with shorter and shorter inter-cell side distance, outdoor, in factories, and indoor. Now there's more that you can do with radio than just connectivity. Mobile networks already know a lot about you. Since generation 1, mobile networks know in which cell you are. That improved, the mobile networks know in which sector you are, power levels. They give you clues on where you are in terms of localization. Beamforming gets even more accurate. And then there are algorithms like angle of arrival and time of arrival that get you to the sub-meter and even to the tens of centimeter accuracy. So couple that with AI, you can infer quite a lot about movement of people, cars, and make predictions, detect anomalies. And RF is actually also an interesting sensor for other things. With assistance of AI, you can actually look at the fingerprint and, for instance, estimate the number of people in a room, analyze what these people are doing, sitting, standing, fall detection. So you can think of applications around building management, energy management, healthcare, elderly care. We even did experiments with radio detecting vital signs. So the radar effect, looking at the chest displacement for vital signs. So again, interesting applications in healthcare and workplace safety. So the 6G, maybe, just coining it, is a network that is going to have a sixth sense. So all this we do to augment machines, to augment human, and to improve the human condition. You can think of it as we go to human 2.0 or maybe even 3.0, depending on how you define it. But the whole idea is that we enhance the human capabilities, the human psychological and intellectual capabilities, thanks to AI processing in the cloud. We enhance human sensing capabilities beyond what the human eye can see, beyond what the human senses can feel. And we enhance our actions through actuators. And all this is interconnected in next generation networks by this critical nervous system, our future network. So as a last slide, I want to reiterate that 6G is for 2030 and beyond. Still a decade away. We still have a lot to do in 5G, many innovations to come in future releases. But time is right to start thinking about the research, and it is important to think also not only about the technology, but the value that that technology creates. And the value is the augmentation of human existence. And I want to conclude with 3 important directions. And I admit we will hopefully already see first instances in the 5G era, but it is a direction to hopefully then see better iterations of that in 6G and future inspiration for future directions. So first is highly specific networks. I made that point that for the future of automation, the needs are very specific for different settings. And so we need to think of the network as a platform with which you can create these different, very specialized instances. Then second, of course, we go for enhanced capabilities in all dimensions, as I gave some examples, and across the whole spectrum. And we are enhancing the spectrum to terahertz, and we also dare to think even of visual light or optical dimension. And then it's not only about connectivity. 6 maybe stands for a network with a sixth sense. So the ability to deduce meaning, to use the network also as a sensor to connect other sensors, assisted with augmented intelligence to deduce meaning and to predict, all to automate, to improve our human condition. Thanks for your attention.
Thank you, Peter. We have time for a few questions now.
Thank you very much for your insightful presentation. I'm from Edge Korea. So you mentioned edge computing in near distance to support low latency. But what if you need some low latency service between the two end devices through the network, like through the internet? Don't you think we need something more to support low latency service through the network?
Okay, so on one hand, edge is one place, and then you talk about hundreds of microseconds if you are within 10 kilometers. We also talk about on-premise clouds, and that's a likely outcome for the future of industrial automation, that you actually have servers on-premise that are then connecting with the devices over the wireless network in the factory. And then what you're hinting at is, of course, you will have on-device processing as well. I mean, we're not saying that it will be a purely processing, it will always be a hybrid. And the other thing I think you were hinting at is you may also have the need for low latency device-to-device communications, and I agree with that, yes.
Thank you very much.
So good morning, Rui Aguiar from Instituto de Telecomunicações. Thank you for your very nice vision of the future. I will have one question, which is slightly provocative, if you don't mind. Hyper-specification, hyper-capable, hyper-sensing, one ring to rule them all. Why do we need a network to do everything and to actually start intruding in areas which have been, until now, handled by different ecosystems with their own specific environments?
A very good question, actually. And the canonical example is autonomous driving. Of course, you can do processing on the car. You have sensors on the car, and you sense your immediate environment. But with high-density cities, there's so much more that you can do when all those cars are connected. You can use information from other cars in the city from around the corner. You can take into account vulnerable road users like bicycles and also have cameras from the city, radars. So you can integrate a lot more. So that is one element. You can do more than just by local processing. Second, it takes a lot of processing power to do all this. A truly autonomous car is actually a data center in itself. So we already talked to the car industry. They say we see value in offloading a lot of these compute capabilities into the edge cloud so that we can make those autonomous driving solutions more cost effective. But it's a valuable point.
Question before we move forward. Your view was for the future is very technocratic, industrial development driven. How do you see softer values? We know that there are lots of challenges to whole humankind these days, and United Nations has these sustainability targets for 2030, 17 different areas. Do you see any value of those, and do you see that those might be driving 6G instead of, or in parallel to this industrial development?
Yeah, I think that future technologies should also, and we have that responsibilities, I think, as an engineering community to make that work. And indeed, sensors can help to have more efficient energy-efficient processes, more energy-efficient cars, sensors that monitor the quality of water, and then also, make everybody connected. I emphasized lower cost technologies also. So I think there's also a responsibility for us to go look into those dimensions.
Okay, now let's thank Peter, give him a big hand.
Okay.
Our next speaker is Dr. Wen Tong from Huawei. He is head of Huawei Wireless Research, and since 2011 he has been heading Communication Technologies Labs at Huawei. He's also Huawei and IEEE Fellow. So, please, Wen.
Okay, thank you, Marty. Thanks, everyone, for your time. What I'm going to talk is about a perspective of the innovation in wireless domain, what could be evolve in the next 10 years. In this talk, what I want to share the view really is not particularly focused on 6G, rather than some much larger trends, what's going on potentially in the technology area in the wireless domain. And because it's a time for the research in 6G, and actually, in fact, the research has to be continued. Action was not really gated by a wireless generation, which is a market realization. In order for every generation, there have to two conditions. From my point of view, there's two conditions need to happen that start to form a generation. The first of all is we need a revolutionary technology. Otherwise, the existing technology will carry on to evolve and to fulfill all the service requirements as people innovate and develop. The second one, which is also very necessary, is a revolutionary applications that will trigger the generation. And for these two to happen or to intercept together, it takes time, typically longer time than 10 years. So for this generation by generation, it's one of the components of the entire wireless evolution history, as Peter mentioned before. So 6G is no exception. It will happen. It's one instant of the longer history of all the picture, a larger picture of the wireless evolution as we see today. So the point is basically what will be the purpose for 6G. From our point of view, the 5G will start and fulfill the connection or the connectivity, almost everything. That is the mission of the 5G, and that is the commercial realization of this year and next 10 years to come. But then the question is, beyond that, is there any larger emerging value or service or the technology development will happen? The one thing is relatively clear and certain now is the artificial intelligence of that technology or AI technology, the pervasive and the scale and the impact of that start to happen. Although this AI technology is not mature as we say today, but it has a bigger potential. And in a larger scale, this has a higher impact. And then the question is there next generation network or some fundamental research we have to do in order to embrace this opportunity? That opportunity potentially can be as big as the internet or even bigger. So that was the question for 2030, and yet we don't know the answer. But if there is a next shift of the generation, is from the connect of the things to the connect of the intelligence. 5G just in a very young stage and it's just happening. There's a lot of life in 5G. So on the left-hand side, that's what the definition of the 5G, and it's the realization of it today. A lot of capabilities, a lot of potential, a lot of these are describing the KPI, and as the industry will start to put this thing into realization. But then, if you go look at the radio capability only, for next 10 years, there are still a magnitude order of the rooms to improve just pure radio capability KPI, key performance indicators. Those are measured every generation by generation, what technology capability of for this particular generation. And then we can see as a step forward for 5G, in the 5G key application or key usage scenario, eMBB, URLC, and MMTC, there's still technology, way for technology progressing and the room for improvement. That means radio is not dead yet. The peak rate, the latency, the density of the connectivity, and perhaps there's some two valuable aspects or facet that people are not very emphasized in 5G discussion is the deep link budget. For example, maybe some 30-40 dB more link budget that will be truly penetration of all the things enabled to do that, and also the use of very high quality radio system to do the positioning. So these are additional value for the radio service. And to be more specific, and from my point of view, with the 5G as the definition of today, there are a few steps to further, natural steps for the further evolution. Because as 5G reach a very diverse application scenario as vertical, especially in the vertical domain, so there's not only one, the use case will fulfill all the requirement for a particular application, especially industry application. For example, they have a mixed requirement, not only specifically eMBB, URLC, potentially these are the two mix. And for the first version of 5G, there are a lot of room to improve the URLC efficiency as compared to eMBB efficiency we have today, meaning there are a lot of solution or standards evolution in order to involve high density, high throughput for the URLC characteristic. This is because at the moment we sacrifice quite a bit spectrum efficiency and redundancy in order to treat for the reliability that industry has this requirement. And then second one is potentially we can see much more wideband Internet of Things, not only the narrowband Internet of Things. The wideband of Internet of Things with the same connection density, a number of huge number of connection is also with a very wide application. Finally, if we can further have a better radio system that with a massive connectivity and a very high requirement of reliability and latency and all the high quality radio system, that will be the desire for fulfill all the especially high-end industry and some new application in this area. So then that's where we're entering some 6G the point. So before even 6G happened, there's a lot of room for 5G evolution. So this is something that academics need also pay a lot of attention. It's a lot of remaining, a lot of technology challenge, and of course, there's also commercial and the product realization in that aspect. So what is really 5G? I get a lot of answer why we have to do 5G, or the question related, why need a 5G, or can we skip even 5G? Those are the questions really comes. So from connected of the people to connected of the thing, there's no way to skip 5G. So 5G is the degeneration truly connect the things. So then from connect people, it's a transformative business innovation, or even sometimes revolution as with respect to the connect of the things. So this is 5G is a very fundamental generation, and it's not a faster 4G, and it serves very different segment of the service and the capability that 5G can offer. So it will become a basic platform for the digital society. Of course, that's the platform for the digital transformation of many service and sector to come. So let's take a projection to 2030. It's not easy because let's say it's often quoted by Bill Gates, that it is often overestimate when we predict 2 to 3 years, but it is often underestimate when we predict 10 years or longer, because 10 years is enough time for revolution and disruption to happen. From the point of 5G and looking for the time of 2030, there are still seems to me is constant. Still need a lot of capacity because the reach of the connectivity of not only the people but things, and also the zero latency or no latency. That's also become even more critical for the growth of the wireless technology into the next generation. And more the wireless network will not be a communication network, but rather than it is some neural network for the society. The control will take much role than the communication from that point of view, based on this infrastructure we have today. And also the fundamental shift in a lot of aspects in radio system itself, also the artificial intelligence will start to play the role. So in the following talk, I will just pick 3 technology that is not mature yet, or it's at a research stage or early research stage that potentially could be shape the next 10 years in terms of impact in the wireless evolution. One more point that I must talk about is the timeline. As the typical generations of the 5G will continue to evolve after really 17 going to next 10 years, because there's a lot of work need to do in that area. And then for talk about 6G, there will be industry and the other community to form a typical exercise in terms of vision, usage, KPI, and what is the timeline. So that will be happening in the ITUR, International Telecom Union. And then we will get into the standardization study in some later stage, 2005 or later. That is the timetable you have to keep in mind in terms of your research. It's a long way to go, and a lot of hard problems and challenges remain to solve. So 6G is not defined by news headline, but this is the hard work we cannot skip. The first area I want come at this point to talk is a bit risky. It is the area when machine learning and artificial intelligence come together to this point. We need to rethink or visit what is the basic of the communication technology, where we need to look even more fundamentally what is the information transmission paradigm. So the left-hand side is very well defined, and we all know in this room that the Shannon structure. He basically deliberately in his structure of framework remove all the semantics and the contexture when they focus on the transmission. So then he breaks down either further to source coding portion and the channel coding portion. So this is basically the blueprint for all the wireless or digital or the communication technology for the past 60 years. But when AI and machine learning come back, and we might need to revisit, is this structure can be further enhanced in order to have more efficiency. One point you can consider is that if there's two machine learning neural networks start to communicate, actually they can learn and start from day one this network getting to life. So they will remember all the past history. They will remember all the conversation, all the context they have before. And when they learn more and they will have a more efficient communication, then the left diagram treat every conversation as a new conversation where there's no context. So this is a very interesting opportunity to go back, combine the learning into the communication at that point. Then there are many fundamental questions open. What is the capacity of a deep learning neural networks? How many they can learn? How many things they can learn? How many past history, past context they can recall with a very simple addressing in terms of communication, or as time goes by, will be smarter. The second question is the channel, or when we exchange the information bit, is it necessary to recover every information correctly, reliably in that context of the communication? Maybe we can lose more, still have a very good communication. We all see this in human and also biological animals. They have a very bad, even very poor condition. They can communicate very well intelligently. So this is another room. Another question, for example, can somebody's a priori knowledge directly transplant to some of the neural network that they carry on with a new connectivity? And these are all the unknown questions in the even in the learning community. So the point I have is, if we perceive or assume AI going to be a bigger thing in the next 10 years later, so this is the time that we need to think more fundamental, how to make a connectivity make relevant to more relevant or more efficient to that type of service and connectivity. I pick two cases that directly apply to the network design, if that is the dominant usage. in 2030. So first of all, unfortunately, the AI, and in terms of neural network, is data hungry. Without big data, there's no, it doesn't make sense for AI as I would say today. And the second is, another problem is very power hungry. So that we will, let's say we presume we will rely on some engineering progression to solve that problem. But if there are so many raw data need to come to the network to make a network become intelligence, and to make every communication entity become intelligence, to transfer this huge amount of bit raw data, or let's say the imaging data, to recognize one thing, you need something, millions of imaging in order to train this new thing to completely understand. So this is a huge burden for the future network if the training in terms of in the network environment, how to reduce that huge amount of data and improve the efficiency. The question is, all the source coding we have researched for past 10 years or many years, or all the source coding standards are designed for the human perception. So is the machine perception, or machine can recognize something, can even make a big loss in terms of compression, and yet the machine still can understand what is the underlying things. There's opportunity, for example, many on a mature theory like information bottleneck theory, that will suggest there's even more times, many more times you can lostly compress the information through the network, and in the cloud the machine can still apply the AI to do many things. And this is a very interesting standardization problem. That means if once we change the source coding standards for the machine learning, and then all these segments can reuse the same data collected. For example, the Facebook will understand in this picture how many people have different relationship, and Google will use the same set of data, identify further information, who is in this room, what is the background or the other information associated with him, or even the police will be interested only particular some criminal people that they want, that it can be still remaining on the first same standard as the data set of this compression. So I think this is a practical and also a very brand new area we need worthwhile to put attention or to put some effort to do this. And then second one is for AI, it becomes smart. Learning takes a lot of time, a lot of latency to train. So then there's a question, again, is the network related to the training or learning? Or it just ship the bits from one end to the other end in the cloud to do this? Or there's some very interesting architecture to put certain learning stage when we have a better picture that is actually can early terminate it in somewhere in the coarse learning or more precise learning on the different network segment. And this will have impact on the network architecture yet to come that we know as of today in 5G. So I just picked these two interesting aspects. It actually is interesting to me that the research community is welcome or should look at this is fundamental aspect, or even in the theoretical aspect. All these points are very high risky, and even we don't have a good theory framework to on top of that. And this connectivity capability can also change a lot of things of traditional service. For example, if 5G really truly can make a video pervasive everywhere as a very good quality, why we still need an operating system in the handset, or why we still need a lot of apps in the handset. So those things can be on the network, completely on the network side. And for this very data demanding, computing demanding, we can reverse back of a lot of apps in the network and probably do a more regional dependent value added service to the consumer, rather than it's the global OTT that is the dominant of the audio application. So this is one thing that could transform the view or the potential capability of the phone. So that maybe the smartphone will be not exist anymore, even for the eMBB application. So the second aspect I want to get in is the terahertz application. Roughly, you do calculation about 5 centimeter or 5 by 5 centimeter area of the array. When you reach terahertz, there will be a million of elements possible to scale down into that array. Then that is a huge potential for this array to steal, to penetrate, and to detect, because the wavelengths of that very, very small wavelengths. And this potential could potentially completely change the phone, because at 1 centimeter by 1 millimeter by 1 millimeter, you will have a subarray with a quite a bit some 30-40 dB gain in terms of a beam. And then if imagine the future phone will be not a phone, it will be everything that's wearable, all this. You basically can sensing a lot of things around you in a short distance, for example, 3-5 meters around. And because of the wavelengths and the resolution of the capability of this new radio frequency, it can completely change the sensing, saying that to unify all the sensing material, your biological condition, your behavior, and easy to think that it will be combined with all the big learning thing on the back end. They can help you to do many things in your life. When you take a lunch or your meal, you can easily sensing all the content, and the machine will advise you what to eat, where you stop. Or they can sense all your biomedical conditions that your health and all the others will improve significantly that we don't see before. In that sense, the terminal or the smartphone will now be a major tool of communication rather than sensing of everything. And because of a lot of science still new in this area, because the wavelengths have this, they can be easily to detect the molecular level structure, vibration, even rotation. Those carry a lot of information. That means you almost have a personal X-ray with you. Go back to the basic radio one. So it will get into some terabits region per second with some new bands. So those are the bands is worth for 10 years later, for example, 6G to explore in terms of data rate and the coverage in that area. So this is one classical evolution or the upgrade of the radio infrastructure we have today. Roughly, these a bunch of new bands that was a new application or new research on this. A lot of technology yet still is in a blank sheet state. For example, higher band frequency, massive satellite. I will mention the satellite technology with some very high band, high millimeter wave frequency, integrating sensing and communication. Those are the one I think it will be very important for the future device, and also for the radio in the lower 6 gigahertz band, and the full duplexes will be mature. That is the latest research results. The third topic, although it is uncertain, but it's very disruptive. So let's take an example. This is already not some not mature technology in the traditional design. For example, if we have 25 centimeter by 25 centimeter with a array, the band is 40 gigahertz. This is the straw man from SpaceX. Their submission to FCC. That assumes a UE size, which could be possible easily mounted on the car. Then the second one is the onboard array size. It's about 2 meter, 2 square meter wide of a panel that in the satellite. What is the key is the amount of a satellite is something 10 or 12,000, not 10 or hundreds of satellites. It's 10,000 satellites in a very low orbit. And in their scheme, the design is about 300 kilometers in the orbit. And the latency is dramatically reduced to something in the millisecond range. And it is let's say it's a 5 gigahertz wide bandwidth. So with this system, because the space technology has dramatically revolutionary by SpaceX, with this system, we can put a simple design of that. The capacity of a single satellite will be something around 1 terabits per second. And then after each beam, remember there's some 64 beam in the satellite, it will be some 19 gigabits per second in the data rate, because the satellite is overpopulated by 10 times at any point of the Earth. So if you do this aggregation like the concept we have today, it will easily reach every beam about some 20 gigabits per second. And then the area capacity is about 32 megabits per second. This is the weak point of this system, meaning that it still need to densify in order to increase the area capacity. But however, because the launch technology is being revolutionized, the cost of the entire satellite constellation, and with this low cost of a satellite itself, because the lifetime is not important for them, for that design is about 2 years lifetime, you can replace the satellite. So that will amount with the capacity and the cost, it almost reached about the terrestrial level, assuming we have 7 million base stations in the populated area, and also the speed is LTE speed. So this is the equation that almost will get there. And this will be for that, as I mentioned, for that 10 years window long potential disruption to change the business or the technology we have. So what they can have is a satellite and a car, and on some larger form factor with a pad or foldable phones. And then it is, the key part is that they are not gold-plated satellite. They are very low-cost satellite. But because the space technology can easily maintain and replace the satellite or launch the new satellite, and the lifetime is not very important. So this is something worthwhile to consider, because it's not within our ecosystem. It's the disruption company. from some other domain. To summarize, there's a lot of new research need to do. What I pick here is what is the AI impact to the network? So the first one is the machine learning versus communication. And it could be fundamental impact for the design of the wireless network system. Second is the higher frequency band in terms of with terahertz range. Primarily not the bit transmission, but yet the other, to unify the sensing or the other application in the handset. That could be potentially a game changer. And the third one is a disruption, not within the wireless industry ecosystem, but some other system, because the revolution of the technologies in space. Thank you.
Thank you, Wen. Do we have questions or comments? Maybe I can start with the first question. As we know, there's now these days a lot of security-related questions related to Asian versus US versus European efforts in building telecom infrastructure. In that respect, I think the satellite-based concept would face serious issues related to security. Do you agree?
I didn't look at this aspect yet in terms of security related to the satellite communication. There are a lot of barriers to even reach that step in terms of regulatory aspect for that to be really commercialized. And also it's a different segment of industry. In terms of security, I don't have any idea. It may be more secure because it's very difficult to intercept the communication between the satellite.
There's another question from.
Yes, hello, very nice vision for 6G. So you touched upon machine learning as a disruptive technology for 6G. You focus more on the on the impact on the physical layer, right? But nowadays, as data is more generated at the edge, typically you don't have time to send this data to the cloud for privacy issues, latency issues, and so on. Which means now we go from this big data to a small data problem, right? So in your view, will that be the kind of game changer in terms of pushing this intelligence to the edge rather than at the cloud?
Yeah, so machine learning, it will happen anyway, irrelevant we have 6G or not 6G. So that's they will have their own evolution path or the progressive path. The matter is how dominant in 10 years later machine learning will be. If it is, then it will be similar situation when 20 years ago we see the internet. Is that the opportunity for the mobile technology to combine with the machine learning? That's what my point.
It's a very nice presentation. This is Ashutosh from Future Network Initiative. You talked about the LEOs. I remember the days when Teledesic wanted to put 840 satellites in the sky back in like late 90s. And I think maybe we're not ready at that point. It looks like we are ready now to have this large constellation of LEOs. But do you think that's sufficient enough? We still have to coexist with terrestrial communication. LEOs may not provide all the bandwidth we need or latency that we need to take care of low latency applications. So there must be a way to coexistence for terrestrial and VLEOs, right?
Oh yeah, so they're still not comparable for the even 5G design as we know today in terms of your LLC feature and potentially the capacity, because these are the early version that's at least 50 to 80 times lower capacity than the average terrestrial network. But it has potential to come in to take certain, to play a role in a certain segment of service. Especially I think the risk is those are the complete closed proprietary system. There will be a proprietary communication system and a proprietary car, for example, Tesla. So it's very easy to mount this some 20 or 30 centimeter size of array to talk with the car satellite with some 30 megabits per second. Then there's a lot of things you can do with that. And the satellite is a global footprint, and the Tesla is a global brand.
Okay, time for the last question.
Yeah. Howard Ben from Samsung Electronics. Coverage is always kind of a controversial subject when we look at standards, because coverage tends to be dominated by money and putting more cells into the network to get greater coverage. At the moment, people don't seem to be willing to pay for additional coverage. Do you think that this is going to change, especially given the very high costs of LEO-based systems? I mean, 10 billion is still a lot of money.
The economics may not change much for the terrestrial. This is probably my view in terms of sites and all the others. There won't be a drastically change. So terrestrial network coverage enhancement is still a challenge. A lot of other things related rather than the radio technology. For the other non-terrestrial network, this is a question. When they come in, they do have a very good capability for coverage, at least outdoor.
Sudhir insists to have the very last question. Can you pass down the mic? Wait for the mic. Can you send the mic down?
My name is Sudhir Dixit. My question has to do more with the two areas that you touched about, use of neural networks and also connecting knowledge, going from the communication network to knowledge networks. When we think about the communication networks, we have ways and means to measure how the communication network is doing through various types of measurement systems. There are companies who are represented here in the summit. But when we talk about neural networks and knowledge networks, how do we measure how one type of system doing better than the other? So, we hear a lot about AI, machine learning, but when you start from zero, you always see a positive improvement. You'll always get good results. But then in a competitive world, how do we measure one system is better over the other? Because we don't know in a self-learning system what is the optimum or what's the objective we are trying to achieve, because that itself may be changing. So my question is more to do with how do we measure, how do we do the performance comparisons of these kind of systems that we are talking about? Your perspective on that.
Yeah, so as I mentioned, this is basically a theoretical in a wake stage. How do you measure? So there are a few things that in the machine learning community they are looking for. For example, in those network, the neural network, there is an information bottleneck that is theoretically connected to the mutual information, meaning that there is a minimum connectivity and the nodes in order to pass this so-called intelligence to the other end. Then you may have so they may have the way to relate to the classical information theory that we have with a solid measure. And then there is some other thing in the learning, as you said, how it's better or not. So the learning people in that way they call the Wiesenstrass as distance. So there are some other we measure in terms of learning. And the point is, are we going to relate it back to the classical information theory? This has to be answered in the research sense. But once those area or the application become the dominant one, rather than important to transmit 0 and 1 bit, so the thing will shift. For example, the voice. It's always some subjective modes in the end that determine your technology is good or not. But this is a very big open area and with a big assumption behind.
I think we have to end the session here. People are already moving to coffee. We continue in half an hour, but before we go, let's give a big hand again to Anne.